Hi everyone, it's Badr speaking. In this video, we will cover a very interesting topic, correlations and dependencies. We need to clearly understand what correlations are and why we must be careful when using such functions. Correlation represents any statistical relationship between two variables. It is not necessarily causal, which makes it sometimes not significant for business purposes. Indeed, we look at correlations to understand the specific link between two variables, and then take action. If we don't know the real reason of this link, it can lead to false assumptions. For example, during summer, there are more skin cancer, and there are more sunscreen sales. We can then find a high correlation between the skin cancer and the sunscreens. A naive assumption is to assume that the sunscreens are increasing the number of skin cancer, whereas it is the opposite. The real reason of the increasing of the number of skin cancer is that during summer there are more sun exposures. Sun is then the cause of a disease. In general, we have to be very careful when we make assumptions. Correlations are very dangerous because of many reasons. The first one is causality. As explained just before, we can make quickly false assumptions and consider the wrong case. There is no perfect mathematical definition of the term correlation. We can easily find monotonic and linear relationships. However, it is much harder to find more complex relationships. For example, a circle which is easy to represent could be very hard to detect. Besides, if we find high correlation between two variables, using a specific correlation function, there is no guarantee that this computation is significant. Indeed, some particular distribution can make the estimation biased, making the score high where it should not. We don't have a perfect correlation function, and few correlation functions exist. The mostly used is Pearson correlation function. It can only identify linear relationship between two variables. For example, there is a strong linear link between the price of an apartment and its area. As Pearson only identifies linear links, we can prefer to use Spearman correlation coefficients. It computes the linear correlation over ranks, making it more robust than Pearson correlation coefficient. For example, the cumulative number of coronavirus cases around the world has an exponential trend. Spearman can easily catch it because of the monotony. However, as it is rank-based, we could possibly have many duplicates, which can make the coefficient not significant. Kendall correlation is ideal for this situation. It is rank-based, but much more robust than Spearman. An example can be to compute the correlation between the customer's rate and the delivery time. We know that the rate will be better when the delivery happens fast. The data will have multiple similar rates, making Spearman coefficient inconsistent. Kendall can handle the situation. If we need to find correlation between two categorical variables, Cramer's V is the only known technique. An example can be basket analysis, where we try to identify links between different articles. A last correlation function exists. It is called Biserial Point. It can be used to compute correlation between a binary response and another numerical feature. A possible example could be computing correlation between churn and the total charges for a telco operator. Almost all the correlation functions scale between -1 and 1. Only Cramer's V range between 0 and 1. When the correlation is near to 1, it means that there is a strong positive correlation between the two variables. For example, the apartment price has a strong positive correlation with the apartment area. When the correlation is near to -1, it means that there is a strong negative correlation between the two variables. For example, the rate has a very strong negative correlation with the delivery time. The rate will be better when the delivery time is low. Finally, when the correlation is near to 0, there is no conclusion to make. Indeed, The two variables might be correlated, but this link is harder to catch. Let's see more deeply how the different correlation functions work. Pearson Correlation Coefficient is really used because of its simplicity. It is identifying a linear link between the two variables. We use it a lot before creating a linear regression model. Let's consider the following distribution. If a linear link exists, it is then easy to find the affine function ax plus b, which can minimize the error. If the estimation is good enough, we can conclude that there is a strong linear link between the two variables. Pearson coefficient can be appreciated because of its low complexity and its easiness. However, Pearson coefficient can only catch linear links, and it is not good with many monotonic functions. It is also very sensitive to outliers. That's why using Spearman Coefficient can be sometimes more judicious. Spearman Coefficient is a measure of the monotonic relationship between two numerical variables. For example, let's take the following curve. There is no linear link and the Pearson Coefficient will not work. But if we consider the linear correlation of the ranks, we place all the data points according to their ranks, the relationship becomes then linear. It makes Spearman Correlation Coefficient very good to get monotonic relationship. It is also very easy to compute. However, Spearman Coefficient can only handle monotonic links, and it is very sensitive to duplicates. That's why some statisticians prefer Kendall Correlation Coefficient. Kendall Correlation Coefficient is also a measure of the monotonic correlation between two numerical variables. However, it is robust to duplicates. It will look at all the possible combinations, find the concordance, here at the tuple leading to an increasing, and the discordant, the ones leading to a decreasing. And it will not count duplicates. By adding one to concordance and by retrieving one for discordant, Kendall coefficient is then analyzing how many times the two variables have a similar behavior. It is computing a score much more robust than the one of Spearman. However, it can only identify monotonic links, and it is very complex to compute. Let's now see how computing correlations between two categorical variables. Cramer's V correlation coefficient is the only one used to measure association between two categorical variables. Let's take the following example. For different weather, some students decided to choose different activities. We can see a huge link between football and when the sun is shining, when it is raining and water polo, and finally when it is snowing and the ski. Cramer's V will analyze this link by looking at the different categories occurrences. It is using very simple rules and can overestimate the strength of association. For example, when one variable has too many categories, the Cramer's V correlation coefficient tends to be very high. Let's now see the last correlation coefficient. Biserial Point is the correlation used to see the influence of the numerical feature on a binary response. Let's consider the following distribution. We compute the average of the two categories, and we analyze if the two averages really differ. We can then get the correlation coefficient. It has a very low complexity, but it is very sensible to outliers. 1 is enough to destroy the significance of the coefficient. When computing a correlation coefficient, we need to be very careful on its significance. We need to compute what we call p-value, which is the probability of accepting the correlation coefficient. Let's try to understand what is p-value using an example. A doctor tries a new medicine to his patients. There are then two hypotheses. H1, the medicine is working. H0, the medicine is not working. He will then define two homogeneous groups and use a placebo for one of the groups and the real medicine on the other. He can then get some success rate of the two groups. He can then compute the p-value. The doctor wants to be sure that the medicine is working. He will then pick a value called alpha, which will represent the probability to accept H0. Most of the time alpha is 5%. If a p-value is greater than alpha, we accept H0 and reject H1. In our case, by choosing alpha is equal to 5%, the doctor wants to be more than 95% sure that the medicine is working. To compute the p-value, we will look at the result of the experiment. And as the result of group A is much greater than group B, we can suppose that the medicine is working. In case of correlation coefficient, our two hypotheses are the following. H1, the correlation coefficient is significant. H0, the correlation coefficient is not significant. For example, let's consider a correlation coefficient of 0.9 having a p-value of 20%. If we choose alpha lesser than 20, we will reject the link between the two variables. You really need to be careful on variables links. They are sometimes very tricky. Besides, having a correlation coefficient equal to 0 does not mean that there is no link between the two variables. Try to always be cautious when speaking about correlation. Let's now see when using the different correlation techniques. Pearson, Spearman, and Kendall correlation coefficients are used to understand link between two numerical features. Always privilege Pearson and Spearman in case of big data, and Kendall for the other cases. Cramer's V correlation coefficient is the only one which can handle links between two categorical features. And Biserial Point can help understanding links between a numerical feature and a binary response. If a categorical variable has many categories, it becomes a little bit more complex. It is then preferable to use a one-hot encoder and compute many Biserial Point correlation coefficients. You can ask yourself, which types of encoding should be used for each scenario? One-hot encoder is really recommended when dealing with a categorical feature, and when we want to use Pearson, Spearman, Kendall, or Biserial Point correlation coefficients. It is even really recommended when using the Biserial Point. We prefer to not split the categories into dummies when computing Cramer's V correlation coefficients. Label encoding must be used with caution. It must only be used with ordinal variables, otherwise the created variable will have no mathematical meaning and the coefficient can be totally biased. When computing correlation coefficients, I really do not recommend to use mean encoding, for the simple reason that it is totally changing the variable. As Cramer's V is sensitive to the number of categories, top K method can be ideal to use on categorical variables. Numerical techniques like Bean's discretizer or user-defined encoding can be used to help computing Cramer's V correlation coefficient, but also Biserial Point if we combine it with one-hot encoding. Let's now see some best practices on preprocessing. Normalization can be used as it can help some of the computations. Downsampling techniques could possibly work if we represent correctly the distribution. However, when dealing with missing values, any technique could possibly add bias to the data. Finally, finding outliers and retrieving them can help having a more significant coefficient. Whoa, now we know many things around correlation. Let's do some hands-on. This is very important to practice to get a deeper understanding. We will use VerticaPy and Jupyter to compute different types of correlations. We will see how creating a database connection, how generating a dataset, computing many correlation coefficients, and understanding p-values. Let's go! Let's use Jupyter Notebook to illustrate this topic. We can connect using a database credential. Be sure to have the same or an upper version to avoid compatibility issues. Let's create the following dataset. We have different people, their age, if they are students, their revenues, their favorite sports, and finally their height, represented by a category. 0 means that their height is lesser than 155 centimeters. 1 if their height is between 155 cm and 165 cm. 2 if they are taller than 165 cm. Let's look quickly at our dataset. We can expect high correlations between different features. For example, age and age, or revenue and each student. Let's draw the revenues as a function of the age using a scatter plot. We can see a clear positive linear link between the two variables. When the age increases, the revenues increase. Let's compute the correlation between the two variables. The correlation is really high, 93%, and the p-value is low. It means that it is highly probable that the two variables are highly correlated. Let's now look at the age and the age. Let's compute the Pearson Coefficient. We can see a high correlation, more than 40%, but also a high p-value. The coefficient is then insignificant, and we cannot conclude on the link between the two features. Spearman correlation is more robust. We can notice a higher correlation coefficient and a smaller p-value. Kendall is even more robust. We can see that a link between the age and the age might exist. It is not so obvious in the dataset as the p-value is still around 5%. However, do not use Kendall correlation coefficient in case of big data. It has a very high complexity. Let's draw a bar chart to look at the link between the gender and the favorite sport. We can notice a link between the two variables. Men seem to prefer football and women seem to prefer dance. Let's see if Cramer's V can find this link. The correlation coefficient seems to be high, but not really significant. The link is not so obvious and it is impossible to conclude. We will need more data to make the computation more robust. Let's now look at the correlation between each student and some numerical features. As it is a binary response, we can use Biserial Point correlation coefficient. Let's first draw a bar chart to see the link. Using the average of each student as an aggregation, the link is clearly visible. It seems that only younger people are students. The correlation coefficient seems to be significant enough, p-value of less than 3%. And there is a high negative link between the two features, which confirm our hypothesis. We can do the same for the revenues and make the same conclusion. But is it causal? According to our experience, we know that if someone is young, there is a huge probability that he is a student. And if he is a student, he may not have higher revenues. We always need to think about the problem before taking action. A number stays a number, and it can be dangerous to use it out of the context. Example: Cramer's V overestimates links easily. The name is just an ID in the dataset. Using Cramer's V correlation, we will find huge correlations with any features because of its cardinality. By looking at the p-value, we can see if the coefficient is significant or not. It's not on those cases. Do it for any coefficient, even Pearson. And only accept the one with small p-value. For example, age and revenue seems to be highly correlated. Always try to be careful when using numbers out of the context. Thank you for watching this video. If you liked it, please visit our GitHub page and add a star to the project. You can also learn more by visiting our website at vertica.com/python. And join the VerticaPy developers community in LinkedIn. See you soon for another video.